before I go on to the non-equal angle, you have any question on this case number 3?
No question, sir.
No question. Okay. No question, then I go on to the fourth case. The two tensions at non-equal angle. If the two angles, okay, right. Now, what is this all about first? Let me explain. Now, it is the same case as case number 3. The, the mass of an object, or the weight of an object, is hanged by two strings. So the two strings, one produce a tension of T2, another produce a tension of T1. Okay, so these two tensions, they are actually pulling back the object, prevent the object from falling on the floor. The difference between case number 4 and case number 3 is that the angle, they are different. The angle at which T2 is pulling and the angle at which T1 is pulling the object, they are equal. They are not equal. So if the two angles, they are not equal, then the tension in rope number 1 and the rope number 2, they cannot be the same. Unlike our previous case here, because the angle is the same, the T and make with the vertical is theta, and the angle T with the vertical is also theta. So if the two angles are the same, then their tensions are the same. In case number 4, the two angles, they are different. Okay, they are different, and the angle, of course, the angles are different. That's why the tension in the two strings, they are different. Okay, right. So if you look at this case, the first force T1 is acting horizontally. The angle with the vertical is 90 degrees. Let me draw this angle with the vertical. Okay, so this is our T1, and the angle is actually 90 degrees. The angle is 90 degrees. The angle with the vertical is 90 degrees. Now this one is T2. The angle T2 mixed with the vertical is theta degrees. One 90 degrees, one theta degrees. We are going to resolve the two forces, T1 and T2, into their components and see whether they and calculate the T1 and T2. Since the object is at equilibrium, that means the object is not moving, it is stable. The net force is 0. So all the three forces, they actually balance one another. If the three forces, they balance one another, that means when we look at the vertical component, the top and the bottom equal. When we look at the horizontal component, the force to the right and the force to the left, they are also equal, right? So first of all, we resolve the tension T2 into two components, the vertical component and the horizontal component. Oh, the angle the angle given is the angle between the force T2 and the vertical. Now you have to be careful with this angle here. Sometimes the angle given is not the angle with the vertical. Let me mark this angle. Sometimes the angle given is not the angle with the vertical. Sometimes the angle given is the angle with the horizontal here. So in that case, the sine and cosine, they interchange. That's all, right? Okay, one more time. The angle given here is the angle with the vertical. So when I resolve T2 into the two components, right, this angle is theta, and this component, the vertical component, is adjacent to the angle. So if it is adjacent to the angle, then this component is T2 cos theta. This one is T2 cos theta. The other component is, which is not adjacent to the angle. There's no angle here. This is not the angle theta. And this component is T2 sine theta. So I resolve the tension number 2 into two components. Now I try to look at the other two forces. The other two forces, they are T1, the tension in rope number 1. This time, the tension is exactly 90 degrees. It is exactly horizontal. So we say that the T1 balance with the T2 sine theta, because these are the two opposing forces. If you look at the vertical component, T2 cos theta, which is acting upwards, and mg, which is acting downwards, and these are the only two forces that is acting on the object. So the two forces, they must balance one another. This means that T2 cos theta is equals to mg. So by comparing the vertical component, we have T2 cos theta equals to mg. Our aim is to find the tension in the string, the T1 and T2. So you have to make the T1 and T2 the subject of the formula. So I want to find T2, I have to bring the cos theta over to the other side. So T2 equals to mg cos theta. Right? So if you replace the mg with numbers and the cos theta with numbers, you can actually find the tension in the string T2. Next, we are going to compare the horizontal components. The horizontal components, they are T1 and T2 sine theta. Since they are acting in the opposite direction, the two forces, they must balance one another because it is at equilibrium. The object is at equilibrium, so they must balance one another. Now, if they balance one another, we say that the T1 equals to T2 sine theta. T1 equals to T2 sine theta. Our aim is to find T1. Our aim is to find T1. So I replace the T2 here with what I have found earlier. What I found earlier is T2 is mg cos theta. So I replace the T2 with mg cos theta. Mg remains as mg, but sine theta divided by cos theta is actually tangent theta. So the T1 is mg tangent theta. Sine theta over cos theta by definition, or you can also prove sine theta over cos theta is actually tangent theta. So this is how we find the two tensions, tension number 1 and tension in the rope number 2. So these are the two tensions that you need to find. Any question on this?
No questions, sir.